Recording, right?
Yeah, I
Okay.
was just caught up in a little bit of something.
Okay, that's fine.
It's
Okay,
fine.
so as long as you're recording, that's cool. So today we're going to be
Yeah.
talking about arrange queries. That's the main lesson we have. So as you see, last week we let me just really quickly recap about last week. So last week we went through search and sort. So that's going to be mostly like the end of the basic algorithm. So like at the start we were doing very basic algorithms. We were talking about how to look at some simple stuff like loops and how to use them um, correctly, how to do stuff like searching and sorting, not really how to do string manipulation. But this is kind of like the end of like the simple algorithms, and we're going to move into some algorithms which are kind of more require you to think a bit more. Like with string manipulation, it's just use this algorithm or use this method, or for example, use this type of list. But it's going to get a bit more, it's going to get a bit harder, and it's going to require you to think a bit more. And it's also going to use a lot more arrays. So that's it. Lists are going to, arrays or lists are going to come in and just become really, really, really important in these future lessons. And like I said, it's not going to be just using something, it's going to be actually implementing some sort of algorithm that can solve a problem. So it's more problem-based learning, if you get what I mean. So it's going to be on range queries. Now, before I start with anything, before Matthew actually starts talking about the prefix summary and everything we need to do, or the range queries actually. So before Matthew talks about range queries, I just wanted to talk about a preface. So this is actually this was the results of, if you're planning to take CC 2021, this was just the results that we got. Thank you for everyone who filled it out. There's 32 responses, and I wanted to point out that a lot of a lot of people actually wanted to do. Actually, this is red. Why am I making this red? A lot of people actually wanted to do senior, right? Like the majority of people wanted to do senior, and most people are, stuck. So let me just really quickly, because I know a lot of people here want to do CC, so I just want to spend 5 minutes talking about this. So if you're unsure about whether you want to do the junior or senior, how you can do this, the simplest way to understand this is just do a problem. So we talked about the DMOD judge a lot, and we leave problems on there, and it's not just like for kind of for show, it's also for you to gauge your own understanding. So something really important that you can try to do next time is just to go on the CC website or just DMOD and pick a junior or senior problem and do it. If you can solve up to like junior 3 or junior 4 consistently, like if you can solve it in like the time limit, then you should probably try senior. If you can't even solve like the first question in senior, maybe you should do junior, right? Like the best way to understand, it's kind of like a math contest. If you don't know what contest you want to do unless you know kind of, I mean, math contests are kind of focused on more grade, but a computer science contest is different because it's not really based on grade. It's more like whatever your ability is. So just go and demolish and try to gauge where you're at, and kind of challenge yourself, right? Like even if you think that junior is still kind of hard, maybe try senior, right? Like it won't hurt if you try senior, even like maybe you're not as good as it, but maybe you can solve a few problems. Try to challenge yourself. But if you're really, really bad at senior and just want to do junior, that's fine too. And the other thing is that a lot of people want to do senior. Now, the thing I want to say about this is that senior is a lot more algorithm heavy. Last week we started talking about stuff like asymptotic growth and like sorting, like searching algorithms, right? We talked about stuff like binary search. That's going to come up a lot more on the senior than the junior. Things that might come up more on the junior are stuff like string manipulation or arrays or data structure. Like these are more junior stuff. Like for example, being able to take a string, parse it, and then do some operations to it, or being able to loop multiple times and get some sort of input, right? That's going to be your junior. That's going to be slightly easier. But the harder junior problems or the easier senior problems or all of the senior problems are going to be more algorithm based, which means that you're going to have a much better understanding of different algorithms that work. So that's just a quick preface of it, whether you want to take the junior and senior or not, and what you do if you're stuck. And that's it. And also to the one or two people who said no, please do it. It doesn't hurt if you do it. Nobody punishes you if you get bad, and if you get good, that's even better because it looks good on your apps. So yeah, that's all I wanted to say. Now, one more thing is that I wanted to highlight the problem difficulty and really how big the problem difficulty ramps up between junior and senior. This is a senior, this is a junior 3. This is a normal junior problem. As you can see, the input specification and output specification are not very big, right? They tell you the values that are given, really simple. Like these numbers are small, right? P is big, but don't worry. The number that really matters is R, and it's really small. So like don't worry too much. It's not a really big number. And the output is really easy too. Just you read the answer and you kind of get it. Now let's look at senior. First of all, you see a lot of these stuff for like 3 of the 15, 2 of the 15, 2 of the 15. Don't worry about this line. That was added in Dmosh. But this really means that the question is split into multiple parts or subtasks, which is what we're going to talk about today. But this is actually a lot harder because if you look at these problems now, look at this number. This number is a lot bigger. And these two numbers both matter. Like this thing doesn't matter as much in the question. But like look at 10 and look at like 20,000, right? Like these numbers are a lot bigger, which means that you'll be dealing with much bigger inputs, which means that if you don't design a good algorithm, it's not going to work. Even if you're perfect at coding and you can code every algorithm perfectly, if you don't design a good one, it's just going to fail. It's getting TLE, like time limit error, and you're just not going to be able to do anything. It's also really important to know that in senior, there are many points that you can get. Like in junior, you either solve it or you don't. It's like a solve or bust. But in this question, it's not really that. You can kind of get partial marks, which we'll also talk about, which means that senior is kind of harder in a way than junior, but junior is also junior is more straightforward. Senior is kind of easier to get simple points, but it's also a lot harder to get full marks on the question. So those are just the problem difficulties. And again, this kind of just also just reiterates what I said. So senior relies more on algorithm design than junior, which means that you have to implement algorithm that will solve the problem efficiently and not just solve it. Because in junior, if you can write the code to solve the problem, you'll probably solve it. Most likely you'll solve it, right? Like it really relies on using the algorithms and implementing them. If you can code it, you can solve it. But senior is different. If you can code it, you might not be able to solve it because if it's not efficient, you just won't get the points for it, right? And in the next few weeks, we'll not only focus on implementation, so like what we've been focusing now on junior, which is just as important, but we'll also focus on algorithm design, which focuses on, for example, big O notation or algorithm implementation, or how we can design a algorithm to solve a type of problem. And that's all I wanted to say about it. So again, um, this is just some differences between junior and senior. And now we'll move on to our lesson on range queries. If there are any questions on the different difficulties or differences between junior and senior, or which one you think you want to take, or if you have any questions about CC in general, feel free to ask any of the CP execs. We'll be happy to answer your questions. And
Yeah.
now, Matthew, we'll start talking about range queries.
So I guess, yeah, I'm going to talk a little bit about range queries, and I want to ask anyone in the audience if they actually know what a range query is before we explain what it is.
Does anybody have a guess what range queries are?
Um, okay. It, okay, Martin, what do you think? And it's,
It's okay if it's wrong. It's completely fine. You're probably not wrong either, because
you're too smart.
yeah, yeah. Ooh,
I guess you can, that is,
that is good. That is good.
it doesn't, oh yeah, it involves a
It
range, and
involves a range, yes, of course. You search for other range, it's close, which is yeah, it's close.
it's
Okay,
close, it's almost there, but not all the way.
yeah. Okay, do you want to talk about definition now?
Okay, I think
Okay,
since no one else speaking up, you can move on now.
okay.
So here, obviously, you can see it's like what Martin said. You search through a range, but not only do you search through it, you calculate some value based on the values in this. You calculate a separate value depending on the value in this range. So you can like sum like the sum of all the numbers within, say, the first element to the fifth element, or the biggest element or the smallest element. And there is a lot of different range trees you can do, but the most popular and the one we'll talk about is called sum queries, and
Yes,
we'll talk a little bit about max and min queries too.
yes. I just want to draw out a kind of quick example, if I can even draw right now, about what a basic query is. In simple terms, it's basically you have an array, right? Like this is what an array mostly looks like. And you basically take an indice, so an index L and an index R. And then you're going to take all these values here, you're going to take them up and you're going to calculate some value. Like let's say if the answer is, we like to use numbers like n. So that's going to be our answer. So we're going to take the numbers here, we're going to calculate something and we're going to print out a value. And that's essentially what a range query is. It's more complicated than that, but that's essentially what we're trying to do. We're taking these values and we're calculating some other value.
So now we can talk about like a problem that we can use a range query for. It's like a bowling problem. Here we have like a number of bowling pins and each one has a score. And then if we knock down each one, say from the bowling pin with point 2 to 5, how many points do we get in total? And there is an efficient way to do this, and there's a really slow way to do this.
Yeah. So basically, yeah, it's you have a bowling ball and you hit down everything from left to right index, and what score can you get? All right, let me see the next slide first. If it's the answer. Oh no, it's not. There's still more
None.
explanations.
So we show this. We can show different examples of different possible inputs we can have, and we're just asking, does anyone have an idea of how you can do this really quickly without having to do the very naive way?
Or if you want, you can just do the easy way. Like think of what just at the start, just think of whatever you have in your mind and just put it in the chat. It doesn't matter yet. Like if you just have an algorithm that you think will solve the problem, you can put in the chat. And if you think you have an even better solution, you can put that as well. But yeah, like Matthew said, we're basically calculating this range, we're taking this value and adding them up. And we're doing this, again, we're doing this many times, right? We're doing this, like in this example, we're doing 2 and 6, 1 and 2, 3 and 5, 0 and 3. We're doing this more than once. Which means that we need to design an algorithm that works, when we ask this question many times. Let's look in the chat. Jump to
Oh,
first index and add each value to a sum until the last index.
oh, I understand. Yeah,
Oh,
that would work.
yeah, that would work. Okay, Matthew, let's see. Do you want to say how? Like, let's look at how this algorithm would work on a simple case. Like, let's just try to
Yeah.
see if this algorithm works. Okay, maybe 3 to 5.
So
3
we
to
start,
5.
yes, 3 to 5. So we start with the 3 bowling pin, which is a value of 2. So we keep adding until the final index. So we have 2 plus 1, then plus 4, which you have a total of 7 points, which is, you can quite clearly see is the answer. So yes, Martin's way would work very well,
Yeah,
or
it would
quite.
definitely work.
Does anyone else have any other way to do it? Okay, I see that uh I see that no one has anything, but you can keep thinking about it because we're not going to reveal the answer right away. We're going to talk a bit more about range, some queries, and then as we're talking about it, you can think of some idea to do this really quickly.
Yeah, but we'll start with the first way that we thought of to solve the question. So let's talk about the problem again. Let's transform the problem into something that we understand how to solve.
So remember how we previously talked about a range sum query? So now we can think of this problem as using multiple range sum queries because we have a left index or the leftmost bowling pin and the
These are
rightmost
bowling pins,
bowling
by the
pin.
way. These are okay. This looks very suspiciously not like a bowling pin. So I'm just gonna do this. This looks like more like a bowling pin. Yes,
Okay.
these are bowling pins.
Yes.
I'm trying to illustrate that these are bowling pins, and then a bowling ball that kind of hits them. Yeah, keep going.
Yeah. So we can visualize this as a range sum query. Leftmost pin is that left indice or L indice, and the rightmost pins are R indice. So now we can do a range sum query to find all we can add up all the sums between those the L and R indices to find the answer we're looking for.
Yeah. So as an example, let's look at an easy example. So what would the sum here be? So like, what would the sum from the index 2 to 5 be in this example? Let's just look at it. Oh, we have another answer.
Ooh,
Some sort of recursion. Ooh, very big word. We are
recursion.
actually, yeah. Ooh, that is actually I haven't even considered this yet. That is a very interesting idea. That definitely, yeah, that would work too. That would work too, right? Because you would just recur down from L to R. That would work too. That is an interesting way to look at the problem for sure, but it definitely works because if you go from L to R, you can kind of recurse down. But if you think about it, the recursion way is actually no, I can't even say that yet because we didn't even talk about a solution. But just
Function calls. You're
Function
gonna
call.
you're
Yeah,
gonna learn to like them eventually.
yep. You're gonna need to do them a lot more. Sadly, you have to like them. All right. So in this example, we're just gonna talk about the sum. We can find how we find the sum here. So like Martin said, we can kind of just add up everything in the list, or like Matthew said, we can add up whatever in the list. So 9 plus 1 plus 8 plus 5. Hopefully I can do basic arithmetic. This is 23. Hopefully I did this right. If that's wrong, you
Amazing.
can laugh at me for not being able to do arithmetic. All right. That was it. So now we're going to talk about the first way that we thought of solving the problem.
So we have the way that actually Martin has the first idea Martin had, which is we just go directly using basically what you can think of as a loop, where we loop through the first index all the way to the last index, and we add all the values together in a sum. However, there is there this method is, how should I say it? This method is kind of quick when you're doing singular queries, but as you do a lot more queries and as the array gets a lot bigger, the the complexity of this approach and the speed really starts to go downhill when you have a lot of queries.
Yeah, exactly. So when we think about it, when you're doing one query, it should be pretty easy to do because let's say you have 3, 1, 4. You're just thinking, well, let me just add it up, right? It's pretty quick, right? I just add 3 elements. But first of all, there are two main things that you should remember in competitive programming. First of all, last week I said that we in competitive programming we deal with very big input. That was something that I said was really important, and you should also remember this for every question. In competitive programming, you deal with very big inputs. So here we draw a very small input, but essentially in the test data, you have millions and billions of inputs. Like this number is just huge. Like you have so many array elements. And if you want to add the sum, you have to add all of these numbers, all of these numbers, all of them together. And this doesn't look like a lot here, but imagine with like a million inputs, you would have to add a million numbers, which is a lot. Right? If you look at this, it's like, oh, it's just 3 numbers. It's pretty quick. But if you have a lot of numbers, it really quickly becomes really big. So let's talk about, but the question really is how big? And let's talk about that. So first of all, how many numbers does it iterate through? It adds r minus l plus 1 numbers. Why? Because let's say we're going from 2 to 5. We need to add 2, 3, 4, 5. We need to add indexes 2, 3, 4, 5, which gives us 5 minus 2 plus 1 equals to 4. So we need to add 4 numbers. But remember, L and R are huge, right? Let's say it's 10 to the 6. Like maybe you go from 0 to 10 to the 6. So it's 10 to the 6 minus 0 plus 1. This is like 10 to the 6 plus 1. Now, this is really big. And if you don't know how big 10 to the 6 is, this is like 1 million. That's pretty big. Or yeah, 1 million, right? Or is it not? It might not be.
It
Oh,
is 1
oh.
million.
Okay, it is. Okay, I was right. I always doubt myself. Okay, it is 1 million numbers. So let's actually analyze the complexity, right? Because we don't really know how fast. Before you can remember, last week we talked about asymptotic growth, because in order to really know how fast something goes, we really have to analyze how fast it goes. Otherwise, we don't really have a way to define how fast something is, right? Like, for example, when you run, you judge it in, for example, kilometers per hour or miles per hour, and that's because you need something to judge how fast something goes. You need to judge speed. And in computer science, we use that, remember? What do we judge speed with? Does anybody remember? What do we judge speed with? Big O, exactly. Perfect. We judge it with big O. And let's look at the big O. So we're going to write 3 big O's. So best case, remember, how do we write big O? So first of all, to analyze an algorithm using big O, we have to do 3 things. So the best case, the average case, and the worst case. And by doing this, we can really understand how fast an algorithm is going. So what's the best case? Matthew, do you want to say the best case for solving this? So like, what would it be and where would that happen?
Well, I mean, the best case scenario, I mean, um, it's a, is, why can't I think of it right now? My brain
It's
is
okay.
getting
It
fried.
is okay. Let's see. Oh, 1, exactly. So
That
do
is
you know
true.
why it's 01? Yeah, it's 01 because the best case is when you analyze one number. It's perfect. So when you analyze only one number, that's going to be your best case, right? Your best case is going to be only when you analyze. It's okay if you have a brain fart. Everybody gets a brain fart once in a while. So if you're analyzing only one element, that's really the best case that you have. And the best case is just O1 because you're only analyzing one element. Now, what would the worst case be? This is important because we're going to look at how important this really is and how this can speed up. Um, what is the worst case of ON? Exactly. Why is ON? Because when we analyze n inputs, the worst case is when we take every element in the array when we add them up. And we know that an array has n elements. So the worst case is ON. And I'll say the average case. The average case is also ON. How do we do this? I'll just remind you again. Next time I won't talk about the average case, I'll ask it to you. But for this time, I'm just going to remind you how to do it. So the average case is best plus worst over 2. So you take ON plus 1 over 2. This goes to ON over 2 plus 1 over 2. Remember, we always take the one with the biggest degree. So this is n to the 1, right? You take the biggest degree. We delete anything that's not n. So we only take this, and we just say ON, right? So that's how we find the average case of the thing, of the algorithm. And again, we can also do this, if you know, big O, there's actually a mathematical way to do big O notation by taking the limit, but again, this is way too complicated for this. We can just use the way that's recommended by most computer scientists by just taking the highest degree and just finding the algorithm. All right, so now that we know the time complexity, now we can now ask, is this fast? So do you think this is fast? Actually, that was a trick question. You weren't supposed to answer that because we still don't know if it's fast because there's nothing to compare it against. Imagine if humans were the only thing living on the earth and we were like, how fast we run. You can't compare humans to anything because there's nothing else that runs, right? Like this is the only algorithm we know, so we can't compare it to anything. How do we know how fast it is if we don't have another algorithm to compare it to, right? Like we can calculate speed, but if there's nothing to compare speed against, speed doesn't matter. Speed is completely irrelevant if there's only one thing that we're calculating speed for, right? So the actual answer is that we don't really care. Exactly. So um,
A lookup
so
table. Hmm.
compare it to lookup table, boom, blown out of the water. Lookup table. That is also a very possible solution. But the question I have for you, Martin, is how would you make the lookup table? And we're going to talk about it later, but that's just a question, an open-ended
Hash.
question. Hash. How would a hash work? It is interesting to say the least.
Oh, you just use that hash map function for
A
Java.
hash map, but then you would have to add them, right? So like when you add everything in a hash map, wouldn't it still take ON? Right? Like a hash map only makes it so that accessing the element is faster. The keys equals to subset. But wouldn't generating the subset also take time? And also, if you generate every subset, wouldn't that take a lot longer? Actually, we're going to analyze this algorithm. You know what? Before we analyze the actual algorithm, let me see if the next slide is that algorithm. And if it's not, because we're probably not going to finish
It's
this in 1 week anyways, it is. Okay,
it
we're going to
is.
analyze this algorithm, Martin's algorithm. So let me just write down ON, and then we're going to analyze Martin's algorithm and see what he means, right? It is a very interesting algorithm. I want to analyze it because it's really, really important because, you know, it's really good. It's also really, really interesting because he's thinking about the question. He's, you know, giving some sort of algorithm to solve the question. So we're going to analyze that. No, of course I wouldn't. It wouldn't take long because you're generating memory error entries. It wouldn't take long, yes, but each entry takes the fastest O1. So even if we assume that a hash map takes amortized O1, it would still take a long time. And I'll actually show that. So basically, let's think of this. So what Martin means is Martin means a lookup table. This is a very, very common way to solve a question, a CEC question. And because we're probably even not going to even cover this because it's not like it's not an algorithm that comes up a lot, but it does come up sometimes. It's called the way to solve it is called memoization. If you know dynamic programming, you're going to say, oh, this is just dynamic programming, but it's not that. It's used in many different places, not just dynamic programming, right? So it's called memoization. So what is Martin implying? So memoization, you pre-generate table, yes, which is So
Yeah.
what is it? It's is ridiculous, but we also want to calculate how fast it is, right? So what Martin's saying is that given any possible L and R, we want to map it to some value K that is the answer, that's sum of L to R, right? That is a very interesting idea because it also looks feasible, right? Well, because if you give me if I pre-process all of the LRs, if I process every subset of LR into some value K, wouldn't that work, right? It would work. It would work. See, this is why these open-ended questions or senior like questions are so hard because they're so open-ended. There's so many different ways to solve it, right? Like here's a way that we probably didn't even consider, and you probably didn't even consider, but it is a valid solution, so we need to check it as well. So when you're doing these problems, really think for what kind of solutions work and analyze them. So let's analyze this one. What Martin means is that you have a 2D array. We talk about data structures, 2D array. So this is L going this way, and this is R going down. And what that means is that he's going to basically, this value is going to contain KLR. Every value here is going to contain KLR. And KLR represents the sum, or SLR. I want to do SLR. It represents the sum from the indices L to R. Now, how fast is this? If we analyze the complexity, every time we calculate this, it takes O1. Great, we're done. We found an algorithm that works. Perfect. Okay, are we done? We're done. We have an algorithm that works faster than ON. Great. Except we don't. Because there's one thing that we didn't really consider, right? There's something that we didn't really consider when doing the problem, and that is how fast does it take to build the array, right? Because when we're doing the naive approach, we build an array of size ON because the array has n elements, and we're basically filling in an array with n elements, and that's just ON. Right? So that's basically how we build an array. But think about this. In this problem, we have to build an array of size ON squared. The answer, actually, the complexity is bigger than O. So I'm going to actually write. So the build complexity is bigger than ON squared. And I'm going to explain why. Because I need to at least touch every element here once. And every element, this has n, and this is n. Which means that if I'm building a 2D array, it takes n squared time to build it. But wait, we're not even done yet, because for every subset, we also need to take the sum from L to R of that sum, which means it's not n squared, it's n cubed. Because if you think about it, every element, this thing also takes n time. Because remember we talked about the naive solution. To add any subset, it takes O(n) time, which means that if we want to pre-process it for every single subset, it takes O(n) cubed time. So it's not O(n) squared, it is O(n) cubed. Let me actually erase stuff so it doesn't look scribbly. O(n) cubed time, which means that, at first we thought, oh, this is O(n), this is perfect, right? This is O(n), this is disgusting. This O(n) is perfect. But we didn't realize that by building the array, you take three orders more time than ON. And let me show you something really funny. And this is probably even more important than the question at hand, because I just want to show you it. Let me just go to Desmos and show you. So
Ooh.
let's say that on a contest, you didn't really think and you just went ahead and solved it. Let's just say that you just use this algorithm, right? Let's see how devastating, or how, well, not devastating, but like how funny your solution would be. Now here I'm gonna graph two graphs, okay? Let's look at these two graphs. Let's say this is Discord. Let's say on a contest, you did the naive solution, which means that you calculated ON time, right? You did this naive approach and you just looped every time and calculated. This is what your graph would look like. This graph goes pretty fast. The blue graph goes pretty fast. Let's say let's just say you're someone else and you're like, okay, I thought of Martin's idea. What if I just pre-process every single thing? You are the red line. Now, if you look at it like this, most people, like I said, when they analyze algorithms, they look like this. They look at this and they say, oh, the red line is so much, sorry, I can't talk today. The red line is so much smaller than the blue line. But then when you scroll out, you're like, oh crap, this is so much bigger. Look at the red line compared to the blue line. Let's just go up and just look at how big this is, right? This red line is growing exponentially orders of exponentials faster. No, you can't look at, yeah, it's less than one. That's not possible. It is, but like even if it crosses later than one, let's say if it even let's say it crosses at like 10, even if it crosses at 10, we're not dealing with inputs that are 10. We're dealing inputs that are like 10,000. So like I need to scroll back like this in order to possibly show you how big the inputs are. And when you look at this input, this is the red line. You're literally going in a straight line, right? So this is why it's so important to do amortized analysis. This is why it's so important to do time complex analysis, because if you don't, you're going to end up with lines like this. And then you're going to be, you're going to be thinking, how can I not even solve a single question? Like I did the perfect solution. It is O1 time complexity. How am I failing this question miserably? Like you're not going to be able to solve any subtask with this, right? You're just going to fail everything. And you're going to be so confused because you're like, my algorithm works, right? It works. I tested it. It works. Why is it going up so fast? And the reason is because the amortized analysis is not only based on the build analysis. Yes, that is very true. If you only do 0.3 iterations, the red line is faster. But like, see, that's the thing, right? It's a joke, but it also really shows how important amortized analysis is, right? Like, if you don't look at it and just look at the O1 and ON, you're like, okay, so if I do 0.3 iterations, it's going to be faster. But it's not, because you don't look at the big picture. And that's really, really, really important. I just wanted to do this because I wanted to show you how important this is. If you can do this, you're going to be able to solve so many more questions than other people. Other people are going to have like, I don't know, 10 points, and you're going to have like 50 points because you can do this. Other people won't be able to analyze algorithms like you can, right? This is the arguably one of the most important skills in computer science, because you need to be able to analyze algorithms properly. Or you're going to fall into the rabbit hole of you think of a really good algorithm like what Martin said, and you think it will work. Well, I mean, Martin didn't think it would work, but like maybe you thought it would work, and then like you do it, and then it just completely fails, right? And you just get so confused. So this is something really, really important that I wanted to touch on, and this is arguably even more important than this question, um, because it really underlines how important um, asymptotic analysis is. All right, that was a very long pep talk. So if you have any questions about what I just said, feel free to ask. Otherwise, if you don't, hopefully this will be recorded and you can go back and listen to my rant again. But
Yes, this is recorded. I am recording.
yes.
So anyway, after that long talk about the time complexity, we are gonna talk about the what is generally think of. Oh, okay, wait. I want to answer this really important question, which someone asked, where can you listen to previous classes? So is yes, there you go, Martin. Come and clutch again with the answers. So we have the Pet CS YouTube channel where we upload videos of our previous lessons. Don't worry if it's sometimes a little slow to upload because some people have some schedule and might be a little hard to edit these videos on the fly, but generally think of the videos coming out within a week or two of the lesson. And see here, Jerry showing off our Pet CS club right there.
Yes, these are like the lessons and stuff. So yeah. Do you want me to put the link in the chat? I can do that. And like
Yeah.
here you have all of your lessons that you want to go back and watch if you want. And yeah, that was it. All right.
So anyway, so now we're gonna talk about the best approach, or not, maybe not the best approach, but the most common approach to this type of problem, where we use something called a prefix summary.
Wait, I'm not I'm not going yet. I was pasting the link. Sorry.
Yes, I know.
Cool.
It's fine.
Yep.
So we're talking about prefix
Yeah.
summaries.
Get us back to this problem. We were talking about how do we improve this solution? Oh wait, before we talk about that, does anybody have any ideas of how to improve this question?
I think it's a
Wait,
bit late.
wait, that was a bit like, but I mean, to be fair, you probably won't search. You probably like without searching it up, right? Like just because I didn't even go to the slide yet. You just said to use a certain algorithm. I mean, like even if you don't, like even if you know what it is, like what is it? Like if you have any
Do you,
ideas to speed it up,
yeah, do you know how it actually works?
other than just saying using a prefix summary, because that would definitely work. Right. If not, we can just start continue. Otherwise,
Yeah, I think
yeah, we'll
I
just
don't
start.
think so.
Yeah,
Here,
so it's kind of
we,
more complicated idea.
yeah, like a prefix summary is like sort of almost exactly what we're looking for here in this type of problem where every value is the sum of all the values before it. So you can see that little graph down there where Jerry showed it, and makes it a little easier to understand. And so this is like very easy, very quick actually to pre-calculate a bunch of different sums. So when you do multiple range sum queries, you don't have to recalculate the sum multiple times. You can easily look up using this table and find the values really quickly. You don't have to calculate the sum multiple times. So this, Martin understands, but there are a few complications where you have to know how to implement this type of array. Does anyone have any idea of how you would implement this type of array? Mm, it's fine. It doesn't seem like anyone really knows it yet, but yeah, we can talk about the,
Walk through the array to build it first.
oh,
Yes, walk through the array to build. Walk through a separate array to build it first. Yes, yes, yes. Keep going.
okay, so we wanna, oh, the source array. Uh, okay.
You can just keep going. We can go back and answer that question. Yes,
So,
just keep
okay,
going.
then, so we want to say like move on. So I have quickly written a piece of code to show off how you would do it in Python. And if you're really curious about how it really works and again in depth, we'll post the slides later so you can like really read it and see how it actually works. But the basic concept is you have a separate array, your answer, and then you just keep track of the sum and just keep pushing it back into your answer array to eventually get the prefix sum array of your original array. Might sound might be a little hard to understand because I use array a lot.
I am unmuted. Yeah, to expand on what Matthew said, basically you have two parts, which is first of all building the array. So building the array is creating the array, and how you would do that is you would first start with a value of 0, and the value is your sum, right? This should be called sum. Doesn't really matter though. I think you get what it means. So basically you start with a sum of 0, and would be the answer array or the result array or what you print to the screen or what you return. And what you do is that for every value in the array, you would add that value to a sum variable and then put it into the answer array, right? You would just put it in, and then you would return it at the end. So for 1, 2, 3, let's do a simple example. So 1, 2, 3, 4, 5. Do you want to go through your code and just explain what it would do at each step?
Oh, okay, sure. So we would start with 1, 2, 3, 4, 5. So we start with our value or sum. Just to note, the reason I didn't call it sum is because sum is a keyword, so I can't use that. Anyway, so we have started with our value with 0, and our answer array is currently empty. So we now go through the for loop. So the first step of our for loop is when I is still 0, and we have the value of the array plus, no, we have the value plus the first array value. Wow, cannot speak either. So we have the value or val, add the first element of the array, which is 1. So now we have value is 1. So we push that back into the answer array. So now our answer array is just 1. So now we repeat.
Wait, oh my God, did I stop sharing? I'm so sorry. I'm so
Okay.
sorry, literally stop sharing. Uh, Wait, give me like 1 sec. I literally stopped sharing. Let me share again. I think I just pressed stop sharing for a second. All right. Yeah, keep
So
going.
so now we move on to the next iteration of our array of our for loop. So now we still have val is 1, and we have our answer array only has a 1 value. So now we repeat. So val plus the second element of the original array, so which is 2. So now val is actually 3. So now we have our answer push we push back 3 into our answer array, so now it's 1 and 3. Then you kind of just repeat that process. Val adds the third element, so now out val is 6, then 10, then 15, and you kind of get the idea, right?
Yes. And one more thing is that to make a query, now that we've built the array, so 1, 6, 10, 10, 15, the next question is how do we build it? How do we test it, right? So first of all, this technically doesn't work yet because we haven't actually returned the array, but you should kind of get what it means. But essentially what happens is that you have the array and then you update it. You technically don't even need a method. You can bring this to like the bottom and just make it a normal program. But essentially what you do is that you can now print, you can basically take the PSA of a value, subtract by PSA of another value. So right, like let's say you have PSA of 3 minus PSA of 1, which would give you the sum of these values. So it would give you the sum of these two values, right? So this one minus this one would give you the sum of these two values. You kind of see what happens here, right? So like when you take one value and you subtract it by another, you get the sum of a certain number of values. So let's say I want to find the sum of 2 plus 3 plus 4. So from here to here, what I would do is that I would take 10 and I would take 1 and I would subtract them. And 10 minus 1 equals to 9. And if you notice, 2 plus 3 plus 4 is also 9. And so that's essentially how you would do the question. Very nicely written code. Let me see if there's anything. No, it's all wrong. Shouldn't
You know
be.
what? Yeah, I was gonna mention Martin's
Yes.
technically right, because as Jerry
Yeah.
mentioned, the test it's not actually test because the
Yeah.
PSA we didn't give the PSA
Yes.
function actual
Yes.
array. So
PSA test. Yes. Uh, this code was like written impromptu, but do you want me to just change it right now? I can just change it right now.
yeah, I guess you could change it to
I mean, to be fair, the most important part of it is honestly like,
the
how do I?
PS.
Yeah, like the most important part of it is like the code. I mean, not really the code, but like the algorithm of how it should be implemented. Like PSA test. Wait. Oh no, PSA test 3, right? Wait.
PSA test and the third indice of that, the return array.
All right. Yeah. True. Okay. So PSA test and then like this. Okay. I am molding. No idea how to solve. I have no idea to write code anymore.
Yeah, and this is generally, yeah, Martin's right. You wouldn't want to build the prefix summary every single time, but we're just quickly kind of like so everyone understands how you would make a prefix summary. It's not really
Yeah.
about really efficiency right now.
Yeah. Um. Yeah. But like to be fair, the most important part is that we're teaching people how to build it. One thing is that like to make this code a lot better, we shouldn't make this a method. We should have made it like part of the original array. So now we actually have an array instead of it just being like a local array. Right? It should be like a global array. But
Yeah, that's true.
if you
But
want a better code, you can go to Geeks for Geeks. They have like really good code of a PSA. But essentially, the thing I want you to take away from this is not really how to, get the value of the PSA. It's more like how this answer is created and how the algorithm is being designed. So like taking, every value and adding it to an answer and then printing it. Again, this is inefficient. There's definitely a better way to do it, but I
yeah,
just wanted to explain basically. And another thing is that going back to this, the reason why the sum is important is because let's say you're taking the PSA4 minus PSA1. What you're doing is that you're taking the sum of 4 elements and you're subtracting the sum of 1 element, which gives you the sum of these 3 elements. And that's essentially how the PSA works, right? Essentially, it's taking any elements and then subtracting the sum of more elements to get your answer. Give me 1 second. How do you check? Do you know how to check breakout rooms? I have no idea.
you check breakout rooms.
Oh, to see if the other people are done yet.
I mean,
Okay, that was just a thing. All right.
no idea.
Okay. Because I have no idea if we need to end yet. But
I mean, I think we have like 13 minutes left.
okay.
So we can, I guess, quickly
Yeah.
go over a few other
Yeah,
things
because I
we
just
have
want to know
left.
how much time we have left. Okay. So 30 minutes left. Let me see how much I want to go to before stopping. Okay. So this is good, and we're just going to talk about asymptotic growth, and that's it. So I just want to again, we're going to go up to asymptotic growth today. CP Java looks empty. Oh, it looks empty. Oh no. Okay. We can just keep going for like a bit more because I just want to finish off with the asymptotic growth and then we'll just finish. If you need to leave now, you can, but otherwise we're just gonna finish off a bit. It's still going as usual. Okay, cool. Well, we'll start then. Okay. Asymptotic growth analysis. So finally, now that we know basically how prefix summaries work and how to implement one, right? Like this is how to implement it. Just move the thing down. Now, how do we actually analyze the time complexity of the algorithm, right? Because the most important thing is not just being able to implement the algorithm, because that will only get you to solve half the question. The most important thing is, can you get it right? Right? So how fast is this algorithm? Right? How fast is a PSA? Let's analyze it. Let's just analyze it. So for PSA, to build the PSA, we build a regular array. And if you look at building the PSA as a method, this basically takes as long as a for statement does, which takes on, right? Because we take each element, so build is on. What about the query? Now, look at how wonderful the query is. We only need to query two numbers, so it's O2. And remember, we only take the coefficient, so it's O1. O2 is the same as O1, right? Remember asymptotic growth. And you realize that this is so much faster because let's look at our previous algorithms. We had like, what was it? What was the previous one? The one the naive one, it was like on and then like on. And this one was like I don't know, n cubed and like O1, right? Like these were the ones we had before. And these ones are like so slow compared to this one, right? Like this is n, it's like n cubed, and this is O1 and this is like on, right? This is so much faster. And if you don't believe me, plug in some value of n and see how fast this grows. Like because n is like 10 to the power of 6. You have a million, you have 1. That is like, it's like this, right? You have this and you have this. Like these two are getting infinitesimally apart. Now, the final thing I want to touch on is how do we actually calculate the complexity of the final algorithm, right? How do we calculate how fast everything is in total? And that's the last question I want to ask. Do you know how to calculate? Do you want to give a guess of how to calculate the algorithm of the final algorithm? It's fine if you don't. It's actually really simple. You just multiply. Just multiply. Or you just add, actually. What am I saying? You just add. Because if you think about it, did you have an answer? Build is one time and access for the main sub. Yes, you just need to add them because if you think about it, O1 is not even based on this, right? You add the build to the query. And like Martin said, we can't just add them normally. Like the easy answer is just add them, right? Like we can definitely just add them, but there's a special way to add them. If you know competitive programming and like you know amortized analysis already, you can just say just add them because people will understand what you mean by just add them. But there's actually a more nuanced meaning to just add them, which means that you actually have to add it based on the query value. So if you think about it, I also have a value called Q. This value was hidden before because we never talked about it. But Q means how many queries we need to do. Because depending on how many queries we need to do, the algorithm gets faster. Now let's look at this part. Let's start with the boring algorithm ONQ plus of this. How do we add this? So first of all, we're going to take the build algorithm, which means we only need to remember, we only need to build one, but we need to query Q times. So we build one, so n cubed, and we need to query one. So on plus q times 1, so which is just q, right? Because we need to do this, we need to multiply this by q because we need to query q times. Now, this is just equal to on cubed, right? We're done because we take the one with the biggest value and we're done. On cubed. Is that right? In fact, it's actually not. It's actually not. The trick is that n and q are different variables. We talked about before that we always had one variable, but now that we have two, we have to treat them separately. So the actual answer is just onq plus q plus onq plus q because we can't really say which one's bigger because n and q can both be really big. And like, let's say n is 10. What if q is like 10 to the 100? Then q is way bigger than n. We have no idea which one's bigger. We can just only show them and we can know which one's bigger. What about this one? Well, in this one, we have on, right? We build it once. And watch what happens now. Every time you have to query n, so plus onq. What about the last one? Does it, do you want to, Martin, do you want to give an, or anybody else, do you want to give an answer to the last one? So how fast would this one be? In big O time, how fast would the last one be? Yes, build this for one time and access T in each subset. Exactly. How fast would it be? O n plus 1. O n, okay, so let's look at it. So first of all, you would say you build O n, right? Uh, any more answers?
No, I think you can just move on for now.
Okay, okay. So O n, and then what you can do is that you have to query every time. So remember O1 multiplied by Q, which is OQ. So you were close. It's not n plus 1, it's n plus Q. Because remember, we're doing querying to every query, right? So this is actually O n plus Q. Sure this stuff is, you actually know for sure this stuff there. Oh, that's fine. You'll get this a lot more and more. I can see that you're more of like a Python knowledge based person. Like you know a lot of like functions and things to do in Python, which is really good. But I think that this is also important to know. Like you, as long as you just do this a lot, you can really get it down. Just like how you know a lot of like Python methods and functions and calls and stuff. This is kind of the same thing, except it's just kind of a different way to do it. But it's completely fine. It should be pretty simple to understand and do as long as you understand how this works. I don't actually know. Math stuff that's fine. That's fine. I mean, it doesn't start out to be a strong suit. It becomes your strong suit when you do it a lot. Just like you probably weren't, Python was not probably not your strong suit when you started out, but since you've done it a lot, you know a lot about Python. This is the same thing, right? When you do this a lot and a lot and a lot, you put in your head and try it and you keep going and you keep going, and you do this like a lot of times, you can really get it down. And that's really the importance of doing anything, right? If you do something a lot of times, you're gonna get it down, no matter how good you are. Yeah, it becomes really important when Bruce mentions it like all the time. But even if Bruce doesn't mention it, you can still kind of put in your head and think about how this works and really get down the concept. It's the same thing of how you're good at Python, right? Like how you can figure out something like an issue in the code because we coded on Notepad. I mean, what? Because you can just understand it. It's the same thing.
Amazing.
Amazing. Yes.
For Martin asked a very important question: who's Bruce?
Yeah.
And that's the
I
link
mean,
he has to give.
anything is the same thing, right? If you put your time into it, you can get really good at it. Just do this a lot. So basically, finally, I just wanted to. Okay, we're just gonna do this. Yes, they have CCP courses. All right, I just want to finish off this in 3 minutes. All right. So basically, we realize that this is a lot bigger. This is a lot bigger than the other few. And what I wanted to end off with is that how big is O n plus q? N times q is squared like this. N plus q is this. And nq plus q is this. Again, we see why it's so important to understand asymptotic analysis again, right? If we zoom out, these things get infinitesimally bigger farther away from each other. And again, we realize that O n plus q is so much better than the other two. Right? At the start, we see that these numbers aren't that big. But remember, in competitive programming, we're dealing with huge numbers. N can be up to 10 to the 6 or 10 to the 9. If you're dealing with computer hardware, N can be up to 10 to the 100, right? There are computer bits that are 10 to the 100. And that's why a tiny, tiny change in an algorithm can drastically change the amount of points you get on a CC question or drastically change how fast your program is, which is why you should really, really master it. Just like Python, right? Like if you can implement an algorithm really quickly, like even on Notepad without failing, like that's a really good skill. And this is the same thing, right? Like if you can analyze some algorithm really, really quickly and just get it down like this, really important. Just like any other skill. And the only way to get really good at it is to practice. Right? There's no other way to get good at anything. Finally, really quickly, again, in the last 2 minutes, we're gonna do a review of everything. And I think my keyboard just died as well. Make sure to get negative values.
Yes, and
Yes, negative. Oh,
you
I
don't
was
need to
using,
see that.
yeah, I was using the, oh, you mean this? I was using that to draw out n cubes because like it's really hard to draw out n cubed by just doing this because n cubed looks a lot like n squared. Like n squared looks like this, but n cubed it's a lot harder because you have to do this. And that's why, I did the bottom part. It was just to help me draw in cube. That's all. All right. So really quickly, again, a final thing.
Yeah, I
So
guess a little final overview
overview.
here.
Yeah, so basically we talk about range queries and what they are. So they're basically values based on indices L to R. We have problems that are based on them, right? So you can take from a left index to right index. And we talk about how a range sum query would basically work and how we would use the naive solution to solve it, right? Just add it up. We also talk about Martin's way of using a pre-processing array, right? And we talk about complexity analysis for that as well. We talked about a prefix summary and how that worked, and basically the intuition behind it of how we add up values and we subtract. Right, and here's a code for it that is definitely not wrong because we definitely did not code it in Notepad. Anyhow,
Yeah,
yeah, and just to change it, if you want to change it again, just take this and just put it on the bottom and just have an answer array in the main program. And then we talked about asymptotic growth analysis, and here's just a slide. I just want to put it here so it's going to come up in the recording as well. But this is a final kind of ending to basically how the time complexities kind of work for each program. As you can see, OM plus Q is way faster than ONQ or previously ONQ plus Q, right? So that's essentially everything we learned. Again,
yeah,
if there are any questions, feel free to ask us on Discord
yeah. Just
or
message
just
us on Discord.
or ask us now because we can stay for like 5 more minutes to answer questions.
Okay,
Inconsistent
fine.
coding.
Be like that. Okay. Python's indenting system's really stupid.
I know. Anyhow, it's not that important. Yeah, okay. But it is true. In yeah, Python indenting system is kind of annoying at times, but
Yeah.
I'm sure we can get over it too. You can get over it.
Yeah, so I guess that's the entire lesson. If you have any more questions, you can feel free to ask us on Discord. And
Yes.
quickly soon, we'll probably post the slides and then post the YouTube video recording. So if you ever need to, you can watch this lesson again.
Yes.
All
Um.
right. So I
Yeah.
guess thanks for listening. See you guys next week.
Yeah. And the next week we'll finish this lesson on other stuff. Yeah. That's
Yeah,
it. Thanks
there's
for
a
coming.
few other things we want to talk about.
Yep.
Bye.
Bye. Time is up for the 60-minute breakout room. Do you want to close our breakout rooms? Let's keep it open for now. Or I mean, should we? Do we need to?
I don't. I close it. I guess I don't see. I mean, I don't know what's going on with intro of Python and whether